Imagine a single mind back in the 1940s, fundamentally shaping the digital world you interact with literally every single day.
It's kind of amazing when you think about it.
Yeah, from the phone in your hand, the AI behind your recommendations, it all points back to one intellectual titan, John von Neumann.
That's right. And this deep dive, we're really going to unpack his revolutionary ideas. He wasn't just the architect of modern computers, though that's huge.
Right.
He was this multifaceted genius. His insights are still guiding cutting-edge tech, especially, in AI.
So we'll explore that foundational computer architecture, definitely.
Yeah.
But also dig into the infamous bottleneck it created.
Mm-hmm.
And then we need to broaden out, look at his contributions across maths, economics, even philosophy. He had early ideas about the technological singularity.
Which is fascinating in itself. So our mission today really is to give you a shortcut. You'll get well informed about this pivotal figure, understand the core concepts behind, well, pretty much every device you use, and see how his ideas, even the ones that seem unrelated, echo through today's most advanced tech. Expect some surprising facts, some aha moments, hopefully.
Okay, so to really get von Neumann's impact, we kind of need to rewind. Before him, early computers.
Yeah.
Well, programming them was just a nightmare, frankly.
Oh, absolutely. Take the ENIS. If
Yeah.
you wanted to change its program.
You had to physically rewire it.
Literally.
Yeah.
Manually rewiring circuits. It was incredibly laborious. Could take weeks.
Weeks just for one program.
Yeah, something like 3 weeks just to set it up and debug it. It was intense.
Wow. Okay, so that's the scene. Then von Neumann steps in. 1945, you said?
Yes, 1945. And he has this revolutionary idea storing both program instructions and the data those programs use in the same memory, using a common bus, a shared pathway.
That sounds almost too simple now, storing them together.
Well, that's the genius of it. It's what we now call the von Neumann architecture.
So what made that specific idea such a game changer? Why was it so fundamental?
Its brilliance was really in its simplicity and, crucially, its flexibility. So structurally, you've got a processing unit, right, that has the ALU, the arithmetic logic unit for calculations, and registers for fast temporary storage. Then there's a control unit that has the instruction register holding the current instruction and the program counter pointing to the next instruction.
Got it.
And all of this interacts with that single unified memory for both data and instructions. It just made computer development much more straightforward.
And cheaper, I imagine. Fewer parts.
Exactly. More cost-effective. And critically, you could reprogram it just by loading new instructions. No physical rewiring needed. Huge leap.
But, okay, there's always a catch, isn't there? This unified approach, it led to something called the von Neumann bottleneck.
Precisely. That's the trade-off. Because data and instructions share that single bus, that single pathway.
Yeah.
The CPU can't grab both at the exact same time. It has to fetch an instruction, then fetch the data, or vice versa. It creates a waiting game, slows things down.
Ah, okay. So it's like a traffic jam on that shared road.
That's a great analogy. Plus, there's another risk. Since they're in the same memory space, data could potentially overwrite instructions. Memory corruption.
Ooh, that sounds bad.
It can be, yeah.
Yeah.
Though there are safeguards, obviously.
But despite these issues, this architecture is everywhere, right?
Yeah.
Our PCs, laptops, phones.
Pretty much dominant, yes. Most personal computers, laptops, smartphones, tablets you use today, they're based on this model. And early machines like EDVA, even the updated ENIS eventually used it.
So if the von Neumann architecture has this built-in bottleneck, what's the main alternative? How did others try to solve that specific problem?
That would be the Harvard architecture. Its core idea is fundamentally different.
How so?
Separate storage and separate buses, separate pathways for instructions and for data. It actually came out of work on the Harvard Mark I Relay computer.
Okay, so instead of one shared highway, it's like having two dedicated highways, one for instructions, one for data.
Exactly like that. So its features are these distinct memory spaces, often fixed instruction lengths, and crucially, parallel access. It can fetch the next instruction while it's working on the current data.
That sounds much faster.
It generally is for certain tasks. It leads to more efficient memory use, especially in smaller, specialized systems. Think embedded systems, microcontrollers, where speed and predictability are really critical.
But it's less flexible, you said.
Yeah, that's the trade-off there. Compared to von Neumann's more general-purpose approach, it's often optimized for specific tasks, making changes harder.
So that parallel access, getting data and instructions at the same time, that's the big win. But what were the downsides that emerged with Harvard?
Well, while it's faster and arguably more secure because data and instructions are physically separate, reducing that corruption risk,
Right.
the main disadvantages are complexity and cost. You need more hardware, basically. Two sets of memory, two separate buses. That makes it pricier. And that limited flexibility means changing or upgrading the system can be trickier. It's often hardwired almost for its job. That's why you see it mainly in things like microcontrollers and digital signal processing.
Right, specialized roles. So if we boil it down, the core difference is von Neumann puts everything together,
Yeah.
Harvard keeps instructions and data separate.
That's the essence. Von Neumann, stored program concept, unified memory, common bus, typically needs 2 clock cycles per instruction because it fetches sequentially.
Fetch instruction, then fetch data.
Right. Harvard, separate memory, separate buses. Can access both concurrently, potentially doing an instruction in a single clock cycle. Faster, but more complex and costly.
Which explains why von Neumann ended up in our general-purpose computers, cheaper, more flexible. Harvard found its niche in those embedded systems.
Exactly.
But that bottleneck, the von Neumann bottleneck, you said it's not just history, it's still a major challenge.
Oh, absolutely. It's arguably the challenge in high-performance computing. At its core, it's that limited throughput, the speed limit between the CPU and memory because of that shared bus.
And CPUs got way faster than memory could keep up.
Exponentially faster. So the processor often ends up just waiting for data. It's idle. John Backus, the inventor of Fortran, he even called it an intellectual bottleneck.
Intellectual? How so?
In his 1977 Turing Award lecture, he argued it ties us to word-at-a-time thinking. We design algorithms based on moving single pieces of data back and forth because that's how the hardware works, instead of maybe thinking more parallelly.
That's a really interesting point. So if it's still such a big deal,
Yeah.
what are engineers doing now to try to get around it?
Lots of clever things. Caching is a big one. You have these small, super fast memory layers, L1, L2, L3 cache, right near the CPU core.
Right, I've heard of those.
They exploit locality. The idea is that if you just used a piece of data, you'll probably need it again soon, so keep it close by in the cache instead of going all the way back to the slower main memory.
Makes sense, like keeping your most used tools right on your workbench.
Exactly. Then there's prefetching. The CPU tries to guess what data or instructions it will need next and pulls them into the cache ahead of time.
So it's anticipating.
Yeah, trying to stay one step ahead. And speculative execution takes that even further. The processor actually starts doing tasks before it knows for sure they're needed, based on predicting which way a program branch will go.
Gambling, essentially.
Calculated gambling. Branch prediction is surprisingly accurate, so it hides a lot of that waiting time.
Okay, caching, prefetching, speculation. Those optimize the data flow. What about keeping the CPU busy with other work while it waits?
That's where multithreading comes in, especially symmetric multithreading or hyperthreading. The OS sees one physical core as multiple logical cores. If one thread stalls waiting for memory, the core can quickly switch to another thread.
Keeping the pipeline full.
Precisely. And researchers are constantly working on new RAM types, too. Things like resistive RAM, magnetic RAM, ferroelectric RAM. They're all trying to improve density, speed, and reduce the energy cost of accessing memory.
So hardware fixes, software tricks.
Right.
Are we also rethinking where the computing happens, moving it closer to the data?
Yes, that's a huge trend. Near data processing, or NDP. The idea is to put some processing capability into the memory or storage itself.
Like processing in memory.
Exactly. Integrate processor logic and memory cells on the same chip. It dramatically cuts down how far data has to travel. Less traffic on the main bus.
And then there's just using specialized hardware, right? Like GPUs.
Right. Hardware acceleration.
Yeah.
Shifting specific, heavy computational tasks to specialized units. GPUs are great for parallel tasks. ASICs, application-specific integrated circuits, are custom-built for one job, like Bitcoin mining or AI inference. And FPGAs, field programmable gate arrays, are chips you can reconfigure after manufacturing. Very flexible for accelerating specific algorithms.
And things like Apple Silicon, the system-on-a-chip approach, that seems relevant too.
Absolutely. So BITISes integrate the CPU, GPU, memory, controllers, everything onto a single piece of silicon. It drastically reduces the physical distance and the need to go across slower system buses for many operations. It's a major way to mitigate the bottleneck at the system level.
Okay, so this bottleneck discussion, it leads directly into AI, doesn't it?
It really does. Because modern deep learning models, running on GPUs or TPUs, fundamentally, they're still running on incredibly fast von Neumann machines, even with all those mitigations.
So the bottleneck is still there, just maybe shifted.
It hasn't gone away. In fact, data movement getting weights and activations to the processing units now often dominates the energy cost and time for training large AI models. It's still the limiting factor.
And that's why we're seeing all these new AI chips.
Exactly. Many of the cutting-edge AI accelerators, neuromorphic chips, they are explicit attempts to finally break or bypass the von Neumann bottleneck, to move computation closer to memory, or adopt radically different architectures inspired by, say, the brain, trying to get away from that word-at-a-time constraint Backus talked about.
That's a perfect bridge, because von Neumann wasn't just about the architecture. His influence was much broader. He thought about the brain itself, didn't he?
He did. It's fascinating. In lectures published after his death, from 1958, he directly compared digital computers, his creations, with neural tissue, with the brain.
What was his take?
He argued the brain wasn't purely digital like the computers he was building. He thought it mixed digital pulses like neuron firing with analog statistical information, and critically that it operated reliably despite inherent noise and randomness.
That sounds incredibly prescient, like he was foreshadowing computational neuroscience.
Totally. And it connects directly to today's neuromorphic hardware chips like Intel's Loihi or IBM's True North, which try to mimic that brain-like structure and processing, embracing analog aspects and parallelism.
And its focus on fault tolerance and massive parallelism.
Yeah.
That also sounds very relevant to AI today, right? Like brain scale simulations or low-precision AI accelerators.
Absolutely. His thinking laid groundwork there. Interestingly, though, he was also apparently skeptical of the very early simplistic formal neural networks.
Oh.
He had this deep thought. He wondered if, at very high levels of complexity, the relationship between logic and the physical implementation might invert. That logic might actually be expressed in the physical effort rather than simplifying it. It's a complex idea, but quite profound for thinking about advanced AI.
Wow. Okay, shifting gears slightly. Game theory. That's another field synonymous with von Neumann.
Absolutely fundamental. You could say he found in modern game theory. Back in 1928, he proved the minimax theorem.
Minimax. That's for two-person zero-sum games, right? Like chess.
Exactly, where one player's gain is precisely the other player's loss. His inspiration, believe it or not, was poker.
Poker?
Yeah, he wanted to mathematically formalize things like bluffing, optimal strategy when you have incomplete information and conflicting interests.
And then he teamed up with Oscar Morgenstern, the economist.
Right. Their book, Theory of Games and Economic Behavior, was revolutionary. It didn't just change economics, it profoundly impacted psychology, sociology, politics, even military strategy.
And the AI connection there seems pretty direct.
Oh, definitely. Multi-agent reinforcement learning, where you have AIs competing or cooperating. They often use minimax logic, just as von Neumann laid out, and think about Jan's generative adversarial networks.
The ones that create realistic images.
Yeah. That's literally a two-player zero-sum game being played between two neural networks, one trying to generate fakes, the other trying to spot them. It's pure von Neumann game theory in action.
He even applied it to the Cold War.
He did. He modeled the U.S. and USSR as players in a zero-sum game, analyzing strategies. And apparently, based on similar logic, he predicted the Allies would win World War II quite early on.
Incredible foresight. Okay, what about Monte Carlo methods? Another area he pioneered.
Yes, alongside Stan Ulam during the Manhattan Project, they needed to simulate neutron diffusion for the atomic bomb, incredibly complex calculations.
Too hard for direct math.
Exactly. So they developed the Monte Carlo method, using repeated random sampling to get numerical results. It showed that randomness, pseudo-randomness on a computer could solve problems that were otherwise mathematically intractable.
And the AI link there is huge, right?
Absolutely fundamental. Monte Carlo tree search was key to AlphaGo's success in Go, exploring the game tree by simulating random playouts. Stochastic gradient descent, the workhorse algorithm for training almost all deep neural networks. That's essentially a Monte Carlo method, taking random steps based on small batches of data to find the minimum of a loss function. Bayesian inference, probabilistic programming, that it all leans heavily on these ideas, using randomness to compute.
Okay, this is amazing, Brett. What about self-replicating machines? Cellular automata. That sounds like pure sci-fi.
It does, but he designed one, a theoretical one, on paper. A 2D grid of cells, like Conway's Game of Life, but much more complex. It had 29 states per cell.
And it could reproduce itself.
Yes, he proved it could construct a copy of itself within this grid world. This work essentially kicked off the field of artificial life, or A-life. It connected computation directly to biological concepts like replication and emergence.
So modern ideas like evolutionary algorithms, maybe self-assembling robots, even things like neural cellular automata used for image generation, they owe debt to this.
Absolutely. They all build on that core insight. Complex, seemingly intelligent or lifelike behavior can emerge from simple local rules interacting in parallel. He even mused about programmable matter and self-healing systems based on these ideas.
Just layer upon layer. We
Yeah.
haven't even really touched on his work in quantum mechanics.
Right. He provided the rigorous mathematical framework for quantum mechanics that's still used today, Hilbert spaces, operators. That work laid the groundwork for quantum information theory and ultimately quantum computing. He was thinking about error correction in quantum contexts too, way ahead of his time.
And connecting the abstract to the concrete. His work on the Manhattan Project. Implosion design for the plutonium bomb. Helping select targets.
Yes, deeply involved. And then, fascinatingly, he turned around and applied similar large-scale computational simulation techniques developed for weapons to weather forecasting, one of the very first uses of computers for complex scientific modeling.
Its range is just staggering. And then there's this term, singularity. He used that too.
Apparently, yes. According to Stan Ulam, von Neumann was the first to use singularity in a specifically technological context, not the mathematical or cosmological kind.
Wow. How did he define it? It feels so modern, tied up with AI now.
Ulam recounted it in a 1958 obituary for von Neumann. He described von Neumann talking about the ever-accelerating progress of technology and changes in the mode of human life, which gives the appearance of approaching some essential singularity in the history of the race beyond which human affairs, as we know them, could not continue.
That is remarkably prescient and captures the feeling perfectly.
It really does, though of course it sparks the ongoing debate. Is progress really accelerating indefinitely, or are we hitting limits?
Right, you hear people saying innovation is slowing down. It reminds me of that Lord Kelvin quote from 1900.
Nothing new to be discovered in physics.
Yeah.
Skepticism about continued progress isn't new.
And how people interpret singularity varies too, right?
Yeah.
Is AGI the singularity or just a step towards something even more profound?
Exactly. It's a complex discussion. And it ties into fundamental questions about computation itself, like the halting problem.
Ah, yes, the idea that you can't have a general algorithm to determine if any given program will eventually stop or run forever.
Right, which relates to a famous von Neumann quote. He supposedly said something like, "You insist there is something a machine cannot do. If you tell me precisely what it is, I can always make a machine which will do just that."
So was he right? Can machines do anything we can define precisely?
Well, it's nuanced. For any specific program, you can determine if it halts. But Turing proved you can't make one machine, one algorithm that works for all possible programs. That's the undecidability. So von Neumann's statement is true for specific, well-defined tasks, but maybe runs into trouble with that universal quantification implied by the halting problem. It highlights the deep philosophical limits of computation.
Beyond the technical, he also seemed to evolve philosophically, didn't he? From a formalist to something else.
Yes, a significant shift. He started out aligned with Hilbert's program, the idea that mathematics knowledge could be fully captured by formal logical systems, predicates, and axioms.
The standard view for mathematicians, then.
A dominant one, yes. But by the 1950s, he'd moved away from that, influenced partly by Gödel's incompleteness theorems, which showed inherent limits to formal systems.
Right, Gödel shook everything up.
And also by his interactions with physicists like Pauli and Heisenberg, who dealt with the messy, probabilistic nature of reality. He became more of an anti-formalist, almost a natural philosopher.
So he started doubting that pure logic could capture everything.
Exactly. He strongly criticized thinkers like Rudolf Carnap and the logicists, rejecting the idea that formal logic alone could adequately describe physical reality. He leaned much more towards empiricism, observation, experiment.
Is there evidence of this shift?
A key anecdote is his advice to Claude Shannon when Shannon was developing information theory. Shannon didn't know what to call his measure of uncertainty. Von Neumann reportedly said, "You should call it entropy. Nobody knows what entropy really is, so in a debate, you will always have the advantage."
Huh. That's pragmatic.
But it also shows his embrace of concepts rooted in physics and statistics, not just pure logic. He started seeing algorithms not just as abstract logic, but as physicalized entities, things that interact with the real world, a contrast to the purely abstract, logical Turing machine.
Interesting. And he was skeptical about purely random processes creating complexity. That anecdote about the villa.
Yeah, the story goes he questioned how something as complex and ordered as a beautiful white villa could supposedly arise purely by chance, like through wind blowing materials together randomly over time. It illustrated his skepticism about purely mechanistic, accidental evolution driving all complex systems. He suspected there might be more organizational principles at play.
And he wasn't shy about critiquing Turing's model either.
No, he apparently considered Turing machines very weak or slow computing models in a practical sense.
Why? Because they operate symbol by symbol on a tape.
Exactly. He felt they lacked computational efficiency compared to his own architecture, especially in handling indexed data structures, accessing memory by address, which his architecture excelled at. He saw his design as much more practical for real-world computation.
Okay, let's talk about the man himself for a minute. The stories about his intellect are just legendary.
Off the charts, by all accounts. Photographic memory people claimed he could memorize phone book pages, recall books he'd read years ago verbatim.
And solving problems on the spot.
Yeah, that famous, "Oh, that," response. Someone would bring him a really tough, novel programming problem, no existing theory. He'd listen, say, "Oh, that," and then apparently lecture for an hour, improvising the entire theoretical solution right there.
Unbelievable. Eugene Wigner, the Nobel laureate physicist, said von Neumann was incomparably intelligent.
Yes, and Wigner added, only he was fully awake. High praise from another genius.
Yet, despite this incredible power, he seemed to have anxieties about what he was building.
Deeply so, especially regarding computers and nuclear weapons. His second wife, Clara Dan, who was a programmer herself, recounted him saying something chilling during the Manhattan Project.
What was that?
Roughly, what we are creating now is a monster whose influence is going to change history, provided there is any history left, yet it would be impossible not to see it through. He saw the immense power, both terrifying and unstoppable. Clara said it wasn't the bomb that scared him most, but the computers needed to build it, the dawn of truly powerful computation.
Wow. And he had his quirks too, right? Not just a brain in a jar.
Oh, definitely not. He was apparently a terrible, reckless driver, supposedly crashed cars constantly.
I heard there was a von Neumann corner in Princeton.
That's the legend. An intersection where he supposedly had frequent mishaps. He also loved parties, telling jokes, could be quite loud and gregarious. Some found his office behavior, like playing loud German march music, a bit disconcerting.
A complex character. Brilliant. Maybe a bit eccentric, profoundly impactful. It always leads to that question, though. Was he the smartest person ever?
Ah, the perennial debate. It's so tricky. How do you even measure that? IQ scores have limitations, especially at the extreme high end. And there's the Flynn effect. IQ scores have generally risen over generations, likely due to better nutrition, education.
Nature versus nurture.
Right. And what about different kinds of intelligence? Von Neumann clearly had an incredible G factor, that general cognitive ability across domains. But comparing him to, say, Einstein or Feynman or historical figures like Leonardo da Vinci, it's almost impossible.
Different eras, different opportunities, different fields.
Exactly. But what's undeniable is that von Neumann operated at the absolute highest level across an astonishing range of fields: mathematics, physics, computer science, economics. His impact was, and still is, immense. He's certainly on the short list, wherever you draw it.
So we've just taken this deep dive into the mind of John von Neumann, a true polymath. He gave us the basic blueprint for almost every computer you touch.
The von Neumann architecture, yeah.
Laid groundwork for AI through game theory, Monte Carlo methods, those self-replicating automata ideas, and even got us thinking about the far future of technology with his concept of the singularity.
It really is an incredible legacy. So for you listening, what stands out the most? Is it just the sheer breadth of what he contributed? Or maybe the enduring power of his architectural choices, the bottleneck included? Or maybe those prophetic glimpses into the future of intelligence?
Yeah, lots to chew on. And here's maybe a final thought to leave you with. Von Neumann himself, he recognized limits. He knew computational systems weren't perfect. They had inherent limitations, potential for errors. He even thought about things analogous to quantum errors way back then.
Right, he wasn't naive about the machines.
So as we push the boundaries now with AI, with quantum computing, Are we just finding clever ways around bottlenecks like his? Or are we, maybe as he might have hinted, starting to uncover fundamentally new physical realities of what computation is and maybe what intelligence itself could be?